Hi everyone, this is Sean. I'm happy to present our work here, Preserving Node-Level Privacy in Graph Neural Networks. This is a joint work with Tianhao Wang from University of Virginia. Both I and Di Wang are from KAUST. Okay, let's have some background first. In our world with exploding data, data in graph form is everywhere. For instance, our social network is a giant graph. And thanks to such a massive amount of data, neural graphs has been a hot topic in the past few years in the machine learning communities. One reason why it has become popular is because the use of graph neural networks, or GNN for short. This allows us to have strong performance on many graph learning related tasks. So let me briefly introduce what a graph neural network is. It is an alternative algorithm that can be summarized by two key steps. The first is that for each node, we gather the information, which is called message, from its neighbors. And the second is to update the node representation vector based on the message. The update function is a simple neural network with numerable parameters. After several rounds of update, we obtain representation vectors for each node. Then we feed them into downstream tasks such as node classification or prediction, link prediction tasks. Although graph neural network has seen many successful applications, it has serious privacy issues. For instance, shown in the upper block, some work has shown that given API access to the learned model, the existence of the edges between nodes that is interesting to the adversary can be inferred with confidence. This is known as the edge-level privacy issue. Fortunately, some work has somehow solved such an issue with an edge-level differential privacy solution. For another example shown at the bottom, given access to the trained GNN model, a membership inference attack against nodes can be performed. However, for this node-level issue, it remains largely unsatisfied. So our work aims to propose a solution for such an issue. We operate under the framework of differential privacy, a robust protocol that guarantees privacy. We formulated the goal of achieving node-level privacy for training a GNN model. Due to the post-processing property of DP, we do not have to worry about the privacy issues when releasing the privately trained model. In our paper, we specifically discussed the formulation for the adjacent graph dataset, which has a specific privacy semantic. Such formulation is due to the feasibility, but we still maintain strong node-level privacy protection. In other words, we ensure that the distribution of the final trained model stays stable up to the removal or addition of a node, including its feature vector, edges, and labels. Okay, our defense method can be classified into the gradient perturbation category, which does not require any convexity of the loss function, contrasting to the other two, which are output perturbation and object perturbation method. So, gradient perturbation. It can be summarized by two key steps. The first is to find the L2 sensitivity of the gradient, which equals to find the maximal impact up to the removal or addition of one node. Then the second step is to calibrate the random noise according to the sensitivity and privacy budget. In the first step, if the gradient has no Lipschitz property, we can just use clipping, which is exactly the DPSD protocol. So what about our problem? If we naively apply step 1, we will only get trivial results. Let's see why. For a tabular-like dataset where each single data is independent from each other, this equation shown in the upper block, the DPSGD protocol, it works perfectly fine. Here we clip, in the summation, we clip each gradient of sampled data points and add calibrated random noise. So if one data was removed from or added to the dataset, we know that there is only one term being affected in the summation, which says that the L2 sensitivity is just the clipping threshold C. Naively applying such protocol in the training of GNN, we can get some some familiar like this equation shown in the bottom, where each gradient for each node representation vector is clipped. Let's do the sensitivity analysis. If one node was removed from or added to the graph, we don't know how many terms in the summations are affected, because due to the message pass mechanism of the GNN, one node can affect multiple nodes' final representations. So this makes randomness calibration hard, which means that the privacy accounting is challenging. Okay, to this problem, in our work, we propose a node-level differential private GNN learning protocol named Heater-Poisson. Our method consists of two main components. The first is a sampler, which contains a special node sampling strategy and a subgraph generating method. The second is a randomizer. We add symmetric multivariate Laplace noise instead of isotropic Gaussian. To have some high-level intuition for our protocol, we control the sampling behavior, and this allows us to track one node impact, which means that tight sensitivity analysis is possible. And finally, privacy accounting or noise calibration is also possible. So let's see what happens if we apply the sampler on some graph dataset. Due to the time limit and space limit, I'm not going to go through every details of the algorithm, so please check it in our paper. The critical point I want to show in this slide is that the outcome the sampler ensures is the following. For any node, it shows up as a central node in the generated subgraph batches. It shows as central node with probability Q, and it appears, and the number of times appearing as a peripheral nodes among the subgraph generated follows a binomial distribution. So that's it for the sampler, so please check it in our paper. And this is a randomizer. The randomizer adds symmetric multivariate Laplace noise instead of Gaussian to ensure DP. We detail in our paper. This is because the tail behavior of such noise. Specifically, we find the noise with sub-exponential tail instead of sub-Gaussian tail only suits our algorithm. So combining them systematically, we have a final privacy guarantee. It is in Rayleigh DP form, but converts to approximate DP easily. This is a snapshot for our main experiment. We tested our method on different datasets and different GNN models. Our method has significant advantages, especially in the high privacy regime. There are also a lot of other experiments we have done in our paper, so please check it in our paper. In addition to our node-level differential private solution, we also provide a negative result for the private node embedding approach that is adopted by previous work for achieving node-level privacy. In this case study, we show that, just as the theorem says, the node embedding approach, private embedding approach has intrinsic utility barriers. Specifically, the classification precision has an upper bound that is related to the privacy budget. So I find this very interesting, so please refer to our paper for details for this case study. Okay, here I summarize what we have done in this paper. We provide a node-level differential private solution, and we also provide a negative result for private node embedding approach used by previous work. The impossibility result just says the fact that the private node embedding approach just doesn't work. Okay, that's it for my presentation. Thank you.